welcome to everyone. Thank you very much for joining us today. I'm super excited about this. I think most of you probably know Dana and have heard him speak before, and that's why you're here. But if you don't know, Dana is a local naturalist and an organic farmer in the Methow Valley and the publisher of the Methow Naturalist. My screen's blurred, so you can't see that, but that's a quarterly publication that comes out, and I will put that information to his website and his email address in the chat so everyone can have that. The chat will be open during the presentation, so if you have questions along the way, put them in there and we'll address the questions at the end. I probably can mute everyone's microphones, but I have not done that. So if you will mute your microphone during his presentation, that will be helpful. And yeah, I've heard Dana speak before, and it's always fascinating. And this is a book that has been on my reading list. And so I'm so excited to get this information. Brief history of our home planet, the geology, biology, and humanity, based on Bill Bryson's book. So thank you so much, Dana. Appreciate you being here, and I'll let you get started.
Thanks, Donna. Yeah, it's been feeling like a difficult assignment, as I mentioned to some who heard me a few minutes ago. It's just a barrage of information and numbers. How many stars you think there are in that galaxy, or what galaxy is it? It's been challenging, but I think I can retain enough. I don't think you want. I have, let's see, 8 pages here. I'm not going to read very much, but I have to refer to it because there's so much information. But there's more information than we need for an hour or 50 minutes or 55 minutes. And it could happen that I'll come to a slide and just skip it. I think there's actually about almost 55 slides. That would be one a minute. So I think, let's see, A Short History of Nearly Everything is one of the most interesting books I've ever read, and I'm sure I'm up to reading it 3 times now, and it's always, every time I read it, I don't remember that I read it before. I mean, I know I read it, but I can't remember the information. It's just a great story. It's cosmic, and the the background to our lives is stunning and incomprehensible. And to some degree, this shows up in these first few pictures. So I like to say this is a picture of the Milky Way galaxy. This is a galaxy. I like to say it's a Milky Way galaxy, but you can't take a picture of the Milky Way galaxy because we're in it. And it would probably take, I have the numbers here and I won't be able to find them. It would probably take 1,000 years at the speed of light to get out of the Milky Way galaxy. This is the Andromeda galaxy. It's a real picture. And the Andromeda galaxy, is 200,000 light years across. So that's 2,000 years at the speed of light. The speed of light's 186,000 miles per second, as you may or may not remember. These are so many of these numbers, they're just incomprehensible. And it's the closest, I think it's the closest galaxy to the Milky Way galaxy, and you can see it with your bare eye, which is really a point of enjoyment to find it. It's somewhere near the Big Dipper. I forget exactly where. I have seen it, but I haven't seen it for about a year. So we live in a similar spiral galaxy to this one, the Milky Way galaxy, and we don't even know how many stars there are in our galaxy. The estimate is 100 to 400 billion stars in the Milky Way galaxy, and we don't know. There's too many to count. If you were to take all of the solid material in our solar system, so now I'm coming down to the area around the sun, which is one, makes up one of the tiny dots in a picture of the Milky Way galaxy. The solid material fills less than 1/trillionth of the available space in the Milky Way galaxy. It's mostly empty space, which is why Bill Bryson said very pointedly, space is extremely well named. There's a lot of space out there, and it's beyond our comprehension to understand the context that we live in. So here's a little side picture of this is the Milky Way galaxy, our sun, and the nearest star is Alpha Centauri, and Alpha Centauri is 4 light years away. So you'd have to travel for 4 years at 186,000 miles per second to get to the nearest star in our galaxy. These numbers are just incomprehensible. If we feel a little bit lost, it's no wonder. It's no wonder. Imagine trying to find meaning in the midst of this infinity of space. So, in terms of seeking meaning, life has evolved over time, and this is a cartoon of vertebrates evolving. That's a fish on the left coming out of the water, evolving into an amphibian. The next one's an amphibian, a reptile, a primate. What are they worried about? Well, this is fairly, in my perception, this is fairly accurate. I mentioned to some of you the chickadees behind me at the feeder. Their primary concern right now is eating enough food to make it through the night because it was 5 degrees here last night. They're not going to reproduce this time of year, but they're eating so that they can survive until summer. I mean, this is just truth. And then one more species evolved from the primate line, and that was Homo sapiens. And we may be the only one of the millions of species on the planet that question what is going on here. And it's, not a bad question. So in an effort to ask the question, what's it all about? Homo sapiens, our species, has created this raft of religions, more than 8,000 religions in the world, many of which claim to know the answer to the question. They tend to be based on stories. It would be hard to have religion without a story, which is, a flow of words in our head that are trying to emulate the physical world, trying to represent the physical world. I mean, one example of what I mean by that is I have a favorite insightful fellow. His name was Krishnamurti. He's no longer alive. Some of you would know that name. But he said, very simply, he said, the word tree is not a tree. None of the things that we create words for are the actual thing. And it's a problem, I think, for us because we live in a symbolic world. So the religions are all made of words, and they're all trying to represent something that either is or is not real. I'm not the one to say, but I pulled this up. Some of you have seen this before. If you've played this game before, you're disqualified from playing it. But how accurate is our perception of the world? So this guy has a card. Just read the card to yourself. What's that card say? And then so what the card actually says, and some of you would have seen the whole thing and some of you would have not, because I know this works sometimes. You'd think the card says you will pick the red card, but what it actually says is you will pick the red card. It says the twice. But information that is fed to our brain that is not relevant or useful, our brain just deletes it. We process the world in a way that we think will be meaningful to us, but in that process, we miss a lot. And I don't know, for those of you who this may have worked and you only saw one you may thereby have an example of the fact that we process the world with our brain. We don't see it as it is, we see it as we are. Famous statement. So here are some beliefs of Homo sapiens over time. It wasn't that long ago that we believed that the earth was flat. You remember that. Not that we believed it, but that was the belief. God made the world in 6 days. That's in the Bible. The begats, that comes up more in the slideshow. These are things that were common beliefs. The earth was only 6,000 years old. And that it was made on a particular day, 6,000 years ago. That's James Ussher, who's in this slideshow later. Certainly people thought it was an Earth-centered universe because we think there's a, I don't know how to express it, but it's natural for humans to feel that things revolve around us. And it turns out they don't. It's kind of a shock. So it was quite a battle in human consciousness to establish the actual fact that the Earth revolves around the sun. The universe does not revolve around us. It's so disappointing. The stars were, people thought stars were holes in a glass dome. They didn't know what they were. How could people know? You look up and you see these little lights. You could go to heaven if you paid enough money. That was the Catholic Church and indulgences. You remember that? These are just beliefs. They're endless. The things that humans believe are endless, but it's good to see that that's the case. So this is, I know, slightly odd, but it has a place. People believe that human excrement should be thrown out on the street for health reasons. Well, that's out of a book called A Green History of the World. And in Europe, they used chamber pots at night. They pooped into a chamber pot. Well, you had to get rid of it. Where are you going to get rid of it? You just throw it out the window. And if it landed in a creek, all the better because it would be washed down the creek. We had no idea of the ecological basis of life. The other animals, for some reason, don't have to think about it. They aren't cut loose from the rules of the planet, but humanity is a little loose. So this is a picture of the world. For some reason, it has a date 1996 in the bottom left. That's or bottom right. That's irrelevant. This is the way we thought the world was in the 1100s, 1200s, 1300s, and before that. It looks it looks like the sun goes around the earth. It comes up in the east, goes across the sky, comes down in the west, comes back up in the east. That's what it looks like. It's counterintuitive to actually realize that the earth is orbiting the sun. And it was a major battle to figure this out. And so people who suggested were very attached to our myths, and many people who somehow figured out that it was a heliocentric solar system, that the planets were orbiting the sun, were put to death. I think maybe, yeah. So this is a true story. Giordano Bruno said in actually, I think it was 10 years before 1600. He did die in 1600. In about 1590, he claimed that it was clear to him that it was a heliocentric universe, that the lights up in the sky were other stars like our sun, and that the Earth orbited around the sun. And he was literally burned at the stake, and he would not recant. He was in prison for 7 years. He's tortured. He wouldn't recant. He said, "It's the truth. I'm sorry, it's the truth. I can't say any different." And they killed him. You remember Galileo was sentenced to house imprisonment for life because he also could see somehow that the Earth was orbiting around the sun. That was only not long after Giordano Bruno. It's a tough road to actually perceive the world as it is. So I guess I should say this program is a bit of a hybrid from big history, which resembles a short history. And I have elements from both in the slideshow. Big history says the universe is on a journey. I don't know if I remember Bill Bryson saying that, but the universe is on a journey. And some of the themes the theme is increasing complexity. Uh, we know somehow, if we wind the clock back, that not only was there no life on Earth, there was no planet Earth, there was no sun, there were no elements other than hydrogen. Science has the brilliance of having been able to figure that out. So these themes arise of increasing complexity, new things emerge. That's a nice one for us because we could use a few new things. We need to step into a slightly greater intelligence. It's possible. Could easily happen. I would say that's a trajectory of the universe. It's a trajectory of our species. Goldilocks effects is a term science uses, and that really refers to the fact that the universe is a strange place and that somehow everything is just right for life to exist on Earth in the same way that everything was just right for Goldilocks. Her chair was just the right size, the soup was just the right heat, the bed felt so good. Everything is just right on Earth. It's mysterious. It really is mysterious. And there are major thresholds that I can't believe I'm doing this without referring to my notes, but it's so hard to refer to notes. There are major thresholds that the Earth passes through. So that's I just pulled up a picture up in the upper left. That is a hydrogen atom. Hydrogen atom has one proton in the nucleus and one electron orbiting around it. It's the simplest element. And it's thought that in the early days of the universe, after the Big Bang, which I don't think there's any understanding of how everything appeared from nothing, we're immersed in mystery. But it's pretty well known that the only element that existed was hydrogen or maybe a little bit of helium, which has two protons and two electrons. There are 94 elements now. Where did they come from? Well, it's an emergent universe. It's always creating new material. So increasing complexity. Here's our hydrogen atom up there in the upper left. And what's going to happen to it? These are galaxies. There were no galaxies in the early universe. There was just hydrogen. Somehow, in ways that it's impossible, I think, for humanity to understand, after the Big Bang, there were hydrogen atoms. And there was gravity. Gravity started to pull the hydrogen atoms together into a mass. They smashed into one another, and they started to fuse into helium, which, remember, is the next element. It has
Fun. We got you in. Okay.
two protons. Two protons instead of one proton. I'm just trying to think here.
Oh, the volume's already up.
So somebody needs to turn their speaker off.
Uh-oh, that's us.
So our star, our sun, is a star. It's fusing hydrogen into helium because gravity has pulled such an enormous mass of hydrogen into a ball that they're smashing into one another and breaking down the barrier of the atom and producing new atoms, which are helium. There's a little bit of mass left over, which is turned into energy, and that's the energy that warms us. It's a fusion reactor. It's not unlike a hydrogen bomb. Hydrogen bombs are fusion reactors. Hydrogen bombs fuse hydrogen into helium, a lot of energy left over. So somehow, in this context, those are a cute little almost cartoon of life down there in the bottom left of bacteria. Life appeared on the planet more than 4 billion years ago. The planet is 4.5 billion years old. There's a little more information on that coming up in the slideshow of where it came from. Life appeared soon. The evidence is life appeared soon after the planet solidified into a solid mass. And there's no understanding of how life arose on the planet. But it has diversified into multiple millions of species. I actually pulled up a little blue whale there. The blue whale just came up in the lower right-hand picture. The blue whale, somewhat surprisingly, is the largest organism that has ever lived on the planet. And I have the information, but I'm not going to be able to find it in the notes. I think when life first appeared, it was single-celled organisms, bacteria, prokaryotes, things like paramecium and amoebas that we recognize the name, single cells. I think a blue whale is something like a quadrillion cells. It arises from a single cell after fertilization. It has all the information embedded in that single cell of how to make a blue whale. It grows in the uterus of the female and is born alive and turns into the largest organism that has ever existed on the planet. It's just all rather mysterious. So I've mentioned this term emergence, which I like a lot. It's an emergent universe. There was nothing. Now there's everything that exists. It's all emerged over time. The whole is greater than the part. So here we have two hydrogen atoms, which remember have one proton each, and oxygen atom, which has 8 protons, and they're gases. Hydrogen's a gas, oxygen's a gas. If you combine them, you get a liquid, you get water. What is that doing there? So new things emerge from the evolutionary cauldron of the universe. Goldilocks effects. Everything's just right on Earth. I have to find. So it has here in the upper left says habitable zone. I wrote down some numbers here. The center of the sun is 27 million degrees Fahrenheit. The surface of the sun is 10,000 degrees Fahrenheit. How would you fare under those circumstances? Space is minus 450 degrees Fahrenheit. The average temperature of the Earth is 59 degrees. It's a habitable zone. If you moved any closer, we would roast. If we moved any further away, we would freeze solid. It's Goldilocks effects. It's a mystery. It's not understood how everything can be there. I have a list going. I probably got up to 25 things on my Goldilocks list, and then I gave up, but I don't think it would ever end. The dynamics that are just right for life to exist on Earth is impressive and mysterious. So the universe goes through stages that big history calls thresholds. Bryson didn't use this term, I don't remember, but obviously the Big Bang is a threshold. We don't understand the Big Bang. We don't understand how everything could appear from nothing, but that's the scientific story, and that's the evidence. Because the universe is expanding, and it was discovered. Trying to think of the name of the astronomer. it's not coming up at the moment, but it was 1929. 1929 is when we discovered that the universe was expanding, that all of the galaxies are moving away from one another. That's not very long ago. Our understanding of the universe is definitely still in process. What happens if you start moving, if those galaxies are moving apart, what if you run the tape backwards and they start moving together? Well, they all come together at a single point, and that's where the theory of the Big Bang came from, that's the evidence, is that everything started from a single point. So that's quite a threshold, nothing to everything. So after the first bang, initially there were no stars. There was just a hydrogen cloud, but gravity pulled that hydrogen together in such dense, intense masses that they started smashing into one another and fusing into helium. And giving off some energy. That's the first stars. The elements, there was only one element, was hydrogen. There's now 92 naturally occurring elements on the planet. Where did they come from? They were created in the heat and pressure of stars. You can't build a planet out of hydrogen. You can't build a planet out of helium. This is a journey that the universe is on. You have to have stars, you have to have the elements created, and then you can have solid ground to stand on. You can't have life without the planet. So these are thresholds that, notable thresholds in the journey of the universe. Photosynthesis might be a little surprising. Anybody who reads a naturalist knows I like photosynthesis. Photosynthesis creates most of the food on the planet. You're not going to have a diversification of life on Earth if there's nothing to eat. Photosynthesis is capturing the energy of the sun in chemical bonds in living organisms. To eat that organism, what's released? What's released is the energy caught in those chemical bonds, which is the energy of the sun. It's the sun that powers our lives. We are literally children of the sun. So, Homo sapiens and abstract thought. That's probably might be a little bit discretionary on my part to have put that in there. But abstract thought, we talked about that a little bit. The word tree is not a tree. It's just a word. But we make a mistake that it is the tree. We think everything that we have words for is the actual thing. It's a problem for us. I mean, it works because we have been able to really uncover the secrets of the universe. We understand how many things work, even at the atomic level. our understanding is true enough that these bombs that we make work, atomic bombs, hydrogen bombs, I mean, they're accurate. Our perception is right. That's abstract thought allowed that to happen. But obviously, it also gets us into a lot of trouble. Another emergent property is intelligence. And we could make fun of that, or we could admire the fact that it exists at all, and that Homo sapiens is on a journey of increasing intelligence. And including that would be ecology. The word ecology means study of the household, if you break the word down. Science of the household, study of the household, how the earth works. That's our assignment. So this is a diagram of the Big Bang. I don't know what I want to say about this, and I better look at my watch. Oh my God. From nothing to everything. So we get this contemplator over there on the right after 4 billion years, 14 billion years of evolution. Star formation, we talked about that. It's an interesting picture. I think it was probably purposely made to look like an eye. But gravity, there was, for some reason, hydrogen existed. Nothing else existed after the Big Bang, but hydrogen did. Hydrogen was pulled together by gravity and formed huge clouds that were compressed and began to fuse and turned into stars. Stars ignite. A little bit about atoms. It's easy to understand. It's surprisingly easy. I mean, so many things are incomprehensible, but what we can't understand is why this is true. But here's what happens with atoms. Atoms have a proton in the middle. We know that, and they have one or more electrons in electron shells orbiting the nucleus, the proton in the nucleus of the atom. Well, electron shells, which is represented here by this black line in this picture, each shell holds a very specific number of electrons. The first shell holds 2. Well, hydrogen only has 1. There is some kind of, I would call it electromagnetic proclivity, drive, hunger for hydrogen atoms to join with other atoms so they can fill that shell. Is that anything like the human heart? I have no idea. To fill the desire of the human heart, I have no idea. But this is a fact. So here's an oxygen atom with 2 electron shells, because the first shell only holds 2 electrons. It's a rule of the universe, 2 electrons. So there's 2, so the electron shell is full. The second shell holds 8. Well, oxygen only has 8 total electrons, 8 total protons, so there's only 6 electrons in the outer shell. It wants 2 more. I think that's what it says here. So you can see there's some potential here. Maybe you could have 2 hydrogen atoms merge or combine with oxygen and share electrons. What about sharing? Synergy. And if 2 hydrogen atoms each shared 1 electron with oxygen, they'd all have their desires filled. They'd have full electron shells, and you would end up with H2O, water. Water is a natural emergent property of the universe. It's built into the original structure of the universe that water would emerge from hydrogen and oxygen. So I wish I had the quote at my fingertips. I have it written down. I've read it many times. But a famous physicist, he won the Nobel Prize. I forget his full name. He said life is probably an emergent property of the universe. If 3 atoms can join together naturally, the complexification, the journey of the universe, is built into the original structure of the universe. Where'd the order come from? Gonna have to go to religion for that. So once again, electron shells, just to point out that the first shell, it says S1, I pulled up a 2 there. The first electron shell holds 2 electrons. If it's not full, like in hydrogen, it would prefer to be full. If has a possibility to combine with another element and fill that electron shell, it'll do so. The next electron shells, shell 2, shell 3, shell 4, they all hold 8 electrons. So if they fill in order up to this point. I think that's right. At some point, they don't necessarily. I think the next shell holds 16. Sorry about that complication, but where did this come from? We have no idea. We have no idea. So I put down at the bottom, the universe, you can fit 10 quadrillion hydrogen atoms on the head of a pin. That's how, gives you some sense of the size of a hydrogen atom, that all have this intricate order to their structure. It's very mysterious. Oh, yeah. So what happens if you were to fuse two hydrogen atoms? This is what's happening in the sun. There's two hydrogen atoms with one electron in its shell and a proton in the nucleus. And if you fuse them together, what are you going to have? You're going to have two protons and two electrons, right? It's called helium. That's how it's done. So, and energy is given off, interestingly enough. Because there's a loss of mass when you combine two hydrogen atoms into one helium. There's a little less mass in the helium atom, and it's transformed into energy, E equals mc squared. Don't ask me to explain that. That's Einstein's formula for energy. Energy equals mass times the speed of light squared. It's ridiculous. So the human body is mostly these elements, mostly oxygen, 65%, 18% carbon, hydrogen, nitrogen, calcium. All of these elements, other than hydrogen, are products of the fusion process in stars. So our bodies are made out of elements that were fused in stars. And this is the scientific fact that we are children of the stars. So we built hydrogen. We were given hydrogen at the beginning of after the Big Bang. Hydrogen existed. To fuse it, you get helium. Well, what happens if you keep fusing? I mean, sometimes chemistry seems rather simple. How about if you fuse? I don't think it's a matter actually of fusing 6 hydrogen atoms together so that you had six protons in the nucleus and 6 electrons in the shells. But if you did have 6 protons, you have carbon. It's just not quite that simple. I forget how the story goes, but it's very arithmetic. Nitrogen, if you have 7 protons, it's nitrogen. If you have 8 protons, it's oxygen. There are 92 naturally occurring elements on the periodic table, and they were all fusion stars except for helium. How does that happen? Well, you need a big press of some kind. That's a lot of pressure. And that is what happens in stars. Look at that. I numbered these. I want to look for the pressure. The pressure at the center of the sun is 250 billion times the pressure of the Earth at sea level. That's how this process of fusion can occur. It's so dense in the center of the sun. And the sun, by the way, is a small star. It's actually called a yellow dwarf. And we have a few other names coming up here of stars. But it's so dense. Gravity has pulled so much hydrogen together that it has that huge amount of pressure, 250 billion times the pressure of the pressure on Earth. And it starts fusing hydrogen into helium. So that's how the elements are made. Here's a piece of the periodic table that goes up to 92 well, it goes beyond 92. I forget if I think it's not even completely agreed if there's 92 or 94 naturally occurring elements. But the last of the elements, if you see at the bottom, they're radioactive. They spontaneously fall apart because they have uranium has 92 protons in the nucleus. They're all positively charged. What happens if you put 92 magnets together in one place? They'll fly apart. They can't hold themselves together. That's why the larger elements are radioactive. They just spontaneously fly apart and they give off energy. And that is both dangerous and useful. But this is where the elements came from. So up at the top, primordial gas cloud. After the Big Bang, hydrogen existed. Why? You have to ask at church. I don't know the answer to that. So red giant stars, red giants are bigger than our sun. As I said, our sun's known as a yellow dwarf. Red giants are fairly large. They have the pressure, the heat and pressure to fuse those elements. Blue stars are hotter. Supernova explosion goes beyond the heat, far beyond the heat and pressure that I mentioned in the sun, and is able to fuse the large elements. And supernovas explode, and they blow those larger elements out into the universe. These elements exist on Earth, so it goes maybe you have to say the Earth could not exist without the prehistory of the universe. There had to be many supernova explosions creating the larger elements, blowing the elements out into space. The universe is 14 billion years old. The Earth is 4 billion years old. So it had the universe had 10 billion years to do its thing. Another picture where the elements come from. Hydrogen's a given. Red giant stars, carbon, nitrogen, oxygen. Hot blue stars, sodium, magnesium, aluminum. And the process stops at iron. I forget why. And the rest of the elements are fused in supernova explosions. It's a very mysterious place. 23. So the Earth accreted from space junk, from supernova junk and supernova explosions after the solar system is only 4 billion years old. The universe is 14 billion years old. So this process of synthesis of larger elements had time to proceed. It's a journey. The universe is on a journey. We get to be part of it. The Earth accreted from the junk that was in orbit around the sun, literally, over time. It was molten. All the heavy stuff sank to the middle. The Earth's core is iron. This is gives you an idea of the size of the Earth down there on the bottom with a little arrow pointing to it. By the way, Pluto's been demoted. It's no longer considered a planet. It's a planetesimal, which means, less than a planet. It's all beyond the capacity of the human mind to comprehend. So the moon is a Goldilocks effect. The moon was created, it's, I think, widely agreed in the scientific community that the moon was created when a planetesimal, a small planet, crashed into the Earth early in the history of the Earth and blew part of the Earth's crust out into orbit around the Earth, which then coalesced into the moon. The strange thing is, when that happened, it blew some of the heavy elements out into orbit. It's thought that the elements in the moon are not the same as the elements in the Earth crust because this explosion blew some of the heavy elements out into orbit. If that hadn't happened, plate tectonics would probably not be possible because the elements that make up the Earth crust are some of the lighter elements. They don't tend to be iron and magnesium and things like that. They tend to be silicon and lighter elements that somehow are able to actually float on the Earth's inner layers. So that might not have happened if there had not been this collision. And without the moon, there would be no tides. There would be, it tipped, I think I have this picture coming up. It tipped the Earth over. The Earth should be 90 degrees to the sun. It's not. It's 23 degrees, 23.5 degrees angle to the sun. This is because the moon knocked it over. If that hadn't happened, there would be no seasons. Every day would be just like every other day on the planet. And the Earth, of course, the Earth also, as it orbits around the sun, it tilts in that 23 degrees changes so that in our winter, it's summer in the southern hemisphere, it equalizes the solar gain around the planet. That's Goldilocks for you. Everything is just right to optimize life on the planet. Nobody understands why that's the case. I think maybe I should speed through this. So we can see carbon has four electrons in its outer shell. It would hold 8. Interestingly enough, silicon also has 4. It has an extra shell, but it has 4. They both hold 8, so they're similar. And I've seen the question asked, and I forget what carbon is essential to life. Carbon gets a bad rap these days, but what was our bodies are like 35% carbon. Very high percentage of carbon. It's critical for life. You would think silicon would work too because but it doesn't. It works for rocks, and that's the point here. So you combine carbon and oxygen and you get a gas, CO2. You combine silica and oxygen, you get a rock. I don't know what to say about that. So this is interesting. I know it's a lot of numbers and it's hard to see, but across the top are the elements: carbon, hydrogen, iron, nitrogen, and then some of the solid structure of the universe down the left column. And I have some circles here. So the Earth crust is not 900%, 1% carbon. It has no carbon in it. But the human body, I think that's what, yeah, look at the human body is 60% carbon, dry weight, if you have to dry out the body. Where's all the carbon come from? And I have a similar one here over on the right. The Earth crust is 28% silicone, but the human body is only 0.2 We have no silicone in our body. Life is different than this, even though we are made out of the structure of the Earth. Life itself is made out of different elements. I'm going to skip that. Oh, I hope we can do this briefly. At least we're up to number 29. So silica is SiO2, like it says there. It's silicone and oxygen. I showed that molecule. The thing about silica is it has silicone, which is SiO2, not silica, silicone. It's a primary molecule in the Earth's crust. It has a low melt point. If you go down that column there, maybe does my cursor show? Silicone has a low melt point. So if you melt rocks, you're gonna get silica. You're gonna get silica before you get heavy elements. So over time, with the heat of the Earth mantle, there has been this process called fractionation, where you heat the rocks and you get more and more silica melts out, and you're left with the heavier elements, which sink down into the center of the Earth core. So you actually have the center of the Earth is actually evolving over time too, and creating less dense. Silica is less dense than magnesium and iron. Silica is what the crust of the continental crust of the Earth is made out of. And it has increased over time because of this process called fractionation. So we've had to figure all this out. What's going on the planet? Why are there still mountains after billions of years of erosion? These were questions until quite recently. Why is sedimentary rock turned upside down sometimes? What causes earthquakes? Why does it look like the continents fit together? This is all stuff we had to figure out. We've had many false starts, many efforts to figure things out. This was an effort in 1664. How old is the Earth? People couldn't help but wonder, how old is the Earth? You can tell how old the Earth is by counting James Ussher, who's an archbishop. Obviously, he was a Christian. You can figure out how old the Earth is by counting the begats in the Bible. Let's see, 31. I wrote down just a few. I can't, because it shows you how much I know about the Bible. Well, let's see. It's not in the right place. Oh yeah. Abraham begat Isaac. Isaac begat Jacob. Remember, it goes on and on in the Old Testament. Well, if you count back, you can tell how old the Earth is. That's the nature of symbolic thought for humans. We can think anything. We can think anything, and we can think that it's true. And it's a pitfall for human beings, the way our minds can be so inaccurate and we're so driven to believe things. So he came up with basically that the Earth was 6,000 years old, and the Earth was created by God in 4004 BC at a certain time on a certain day. We're just trying to understand things, and it's the nature of the mind to just make stuff up. James Hutton is known as the father of modern geology. Obviously lived in the 1700s. And he figured out that the Earth was dynamic. He just put two and two together. Why are there shells at the tops of mountains? There are marine shells at Hart's Pass, for instance. We have this very phenomenon here in the Methow Valley. Shells on many of the mountaintops around here. What are they doing up there? That's what Hutton figured out. He understood that the Earth's core and mantle were molten. The volcanoes were supplying all this heat. And he was the first to suggest that the Earth was actually hundreds of thousands of years old, which shocked people, and that there was this geological process underway that was transforming the face of the Earth, going on all the time. So we came up with time. Now we had, after Hutton, there was time for the Earth to evolve. And this geologic chart was created that has, I think I have, oh, they're out of sight up on top there. Eras and periods. So that down the middle there's Paleozoic. Well, those things all mean something. Paleo, we know the word, it means old. Zoic, it means life. Paleozoic means old life. It helps so much when you're faced with all these words to realize they have meanings that we can understand. Mesozoic, meso means middle, middle life. Cenozoic, I think Ceno is recent, recent life. Same thing with the periods. The Pleistocene, I have it written down. I kept trying to remember. Holocene means like holy now, not with an H, but with a W. Holy now, right now. Holocene is right now. We're in the Holocene. Pleistocene means something like almost now. They really do. That's close to what they mean. But at least they mean something, and you can get them translated. But what we came to understand is that life has this history, and we can put it together. And there is a similar chart for the Methow Valley, which I can email you if you want it, and I'm going to blow it up here so you can see what it says. But it's our understanding of the history of the Methow is the same, based on the same information as understanding of any place on the planet. So here are the same eras. I mentioned Cenozoic, Mesozoic, recent time, middle time, Paleozoic, old time. The geologic periods, those all exist here too, and different things happened at different times in the Methow. I can read this. So 6,000 years up here at the top right, 6,000 years before the present, the approximate date that salmon first appeared in the Columbia River system. Well, there was an ice age before that. There was so much sediment coming down in the rivers that there were no salmon in the rivers. So it's just that the Methow Valley has an evolutionary history in the same way that any place on the earth does. 35. I'm going to speed up. I think we want to be done in 8 minutes. Everything that we know about the earth had to be learned, had to be discerned, figured out. The fact that the continents move was a shock. I have some quotes here when Alfred Wegener figured out that people understood. Well, what it shows here down at the bottom, it shows a map by Abraham Ortelius in 1596. He could see that the continents looked like they fit together like a jigsaw puzzle, and he suggested that the continents had once been together, and that the big great flood in the Bible, because that's the way the mind works with these stories, had ripped them apart. So that was 15, 16, 17, 18, 19, 400 years ago. So Wegener studied the coastlines of these African and South American continents. He found they had the same rocks, they had the same fossils, they clearly had been connected. And I think, so he came up with the theory of continental drift, that continents moved. It was, I have a quote here by some scientist who said it's complete and utter rubbish. At the time, he said that it happens to be well established that the continents drift over the surface of the Earth's surface over time. But it was a struggle to have that accepted. We have these belief systems, and it's very disconcerting when our beliefs are disproven. Then it was found that the ocean crust is different ages. And that's what these colors show. The sort of pea green near the continents, it shows down the bottom was somehow, well, what was found was that there's a rift in the middle of the Atlantic Ocean, and there's a rift in the Pacific Ocean, and there's magma pouring out. So this was found during World War II and after World War II. So 1940s and 1950s, magma was pouring out of these rifts and pushing the ocean crust apart. And so the crust had different ages. The new crust was always at the center where the magma was pouring out, and further out, and that people were able to pull up some crust and age it, and they found out that it was, some of it was 5 million years old, 10, 20, up to 140 million years old, and then it disappeared. It got up against the continents and disappeared. Well, that had to be figured out. Here is the ocean crust with magma. It's pushing the ocean crust apart. Fresh magma is always coming out. What happens to the crust when it reaches the continent? That was a question. Was finally figured out that the ocean crust cools as it's pushed away from the mid-oceanic ridge, cools, gets heavier, and sinks under the continents, which are made out of that high silica rock, which are lighter. They actually float on the upper mantle, and the ocean crust subducts and is remelted in the mantle and then reappears in volcanoes. So all this has been figured out, and it's relative to the Methow because this is the structure of the Methow Valley. On the upper picture, there's sediment running off the continent by erosion over time. There's a ocean crust is subducting under the continental crust because it's heavier. It has a piece of land stuck on it called a terrain, and the terrain is pushed up against the continent and accretes, and anything that's in between gets smashed. And so if you look at the sedimentary rocks in the Methow, this is on the highway right by the Winter Post Office. The sedimentary rock is turned 90 degrees up in the air. Same with Virginia Ridge. This is because of plate tectonics. Why is it hot? Because of radioactive decay. We had to figure that out. There's a lot of radioactive elements in the Earth's crust. They decay spontaneously. They have too many protons in the nucleus. They decay over time. They have a certain lifespan. They give off heat. I think I didn't. I'm trying to put in energy. They give off energy, and that's where the heat comes from. Down below is that planetesimal striking the moon. These are all, everything is just right. So what you end up with is the nutrients and elements of the earth running into the sea as sediment, collecting in the sea, being solidified into ocean crust, subducting under the continents and reappearing at rift zones and volcanoes. So the earth recycles everything that runs to the sea. Goldilocks could not have done it better. Here's a ring of fire, or the ring of volcanoes, because of plate tectonics and subduction, because of the oceanic rift down the Pacific and down the Atlantic. There's a row of volcanoes. Here are some volcanoes. I circled Tambora over on the left because it blew in 1815. It's one of the biggest eruptions in the last 200 or 300 years. There was a volcanic winter in 1815. Crops failed all over the planet. There was so much dust in the atmosphere after Tambora blew. At that time, there were 1 billion people on the planet. Now there's 8 billion. What's going to happen? We don't know. So this is the same phenomenon of plate subduction under a continent carrying a landmass on it called a terrain. The word's down the bottom there, Terrane. And when the crust carries the terrain onto the continent, the terrain is made out of the higher silica rock. It does not subduct, it's accreted. So continents have grown over time. And these are all terrains. The whole west coast of North America, including, look at Alaska, is all terrains that have accreted onto the continent over time because of the process of plate tectonics. Look at that. What self-assembles? We have that's a hydrogen atom in the upper left. The sun assembles out of hydrogen atoms. It produces the elements that are in the periodic table. The Earth is made out of elements that were fused in stars, and somehow life appeared. We don't know how, but the largest creature that has ever lived on the planet is that blue whale down in the bottom. So this is an interesting, we are almost done. This is the self-centered mind. It's natural to be, so all organisms are self-centered. It's very natural. but it might not be the most accurate perception of the planet to, as we saw earlier, when we thought that we lived in a sun-centered universe because everything has to go around us. It turns out everything doesn't, that we're a part of something much larger than ourselves, this evolutionary journey. It's called ecology. I almost took this out, but I left it in. Who's this? Oh, Calvin and Hobbes. I tried to decide whether to cheat or not. Would it be better to cheat and fail, or do the right, do the right thing and fail, or cheat and get things wrong? And I put this in because of the question of ethics. We started out with hydrogen. All there was in the universe is hydrogen. Where did right and wrong come from? Where did truth? Where did something that's actually true? Where did that come from? We just all started with hydrogen. There's something going on in the universe, and we get to be part of it. I'm going to skip this because we're out of time. That's just, I like this picture. This is a picture, a real picture of the Earth from space. This is Carl Sagan showed this picture of mote dust suspended in a sunbeam. All of the drama of our human lives. It puts it in perspective. This is where it takes place. This is our everyday miracle that we get to enjoy, the beauty of planet Earth. And we are, it says at the bottom, we are not on the Earth. We are actually made of the Earth. We have evolved from the dynamics of the Earth. So congratulations to you. And if you want, some of these stories are in the Naturalist. Oh, I survived. I'm so glad. Chat.
You
Any
did. Thank you so much, Dana. That was amazing and overwhelming. It's overwhelming to think about. And
Yeah, it is overwhelming. It's incomprehensible.
Yeah, I'm
Yeah.
thankful, and the Goldilocks effect, which it seems like are not really explained, but very thankful for the moon creating the seasons.
Yeah.
And
Good.
I loved your ending, kind of putting us in perspective. Yeah, it has been so long held that we are the top of the chain, and it's obvious that that's not true. Yeah, we're just a
This
small
is
part.
Julie. Can you hear me? Can you hear me?
Yes.
I want to add the planet Earth is the only planet that sparkles in this solar system because we have water,
Yes. Yes.
H2O.
Yeah.
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 Yeah, that is amazing. Dana, I will share that we did get the question about whether these would be recorded, and this has been recorded, and I will work on getting it onto our YouTube channel when I figure out how to do that.
Okay.
We do have a question here from Jerry. Are there any theories why Earth and most of the other planets turned out round instead of just ragged shapes?
Interesting question. Uh, so it's interesting then the process is I get to think about it, everybody gets to think about it, and that's the human mind at work. And can we figure this out?
Well, maybe that's an answer that we can you can research for next week.
You can definitely Google it.
Yeah, yeah.
Or ask.
Andy also pointed out that Mars has water as well.
Right. Not very much, but some.
Yeah.
It's
Well,
hard to retain water because hydrogen is the lightest atom, as we've established, and it's therefore not held by the gravity of whatever planet it's on. Everything is held down by gravity, or it floats off into space. If there was no gravity, everything would just dissipate. So we lose hydrogen. There's hydrogen in the atmosphere, and some of it is lost to space, and we could lose our water over time. But I wouldn't worry about it right now.
Yeah. Well, we certainly need it, don't we?
Yeah. Oh, I didn't have a chance to say, but I think the human body is something like 35% water. And next to that in my notes, I have that watermelon is only 60% water. So we're not that different than a watermelon. I kind of like that image.
Oh, interesting.
We're
Yeah.
very, we're
I'll
very,
share another comment from Stephen. He came in late but learned something new. The process of accretion of terrains was new to him,
Oh, yeah.
and we'll be looking at soils and regions differently now. Yeah. Well, I will just share that Dana has made his email available to all of us. If anyone has any follow-up questions they'd like to reach out, it's dana@metoutnet.com. And you can reach out to him directly. And also, we will look forward to seeing you all again next week for more. Jerry's just added that there is a Google answer. Why are the planets round? Because their mass is large enough to generate gravitational forces large enough to beat the angle of repose of most materials over time. All of the planets are round, or more accurately spherical, because of gravity.
Thanks. I'll buy that.
Yeah. Well, thank you so much, Dana, for all of this great information and for giving us an overview of what's included in the book. And we will look forward to meeting again next Tuesday at noon for more.
Thanks, Donna. Thanks for making it possible.
Thank you, Dana.
Yeah, thank you so much.
Thanks, Sue. Thanks, Dana.
Yeah. Take care, everybody. Be
Thank you. And there's many messages of thanks, Dana.
Okay. I can't see anything.
Okay, well, I will go ahead and stop the recording and sign off. And Dana, I'll talk to you before next Tuesday.
Okay, sounds good.